Casting the solutions to lab 3.1p. I'm going to, as I do this, really just make up some of the predicted answers that you might have received during the lab. So as we go down through this, let's just go one by one. So in part one, the predicted vortex times for the solutions. Now we're going to assume that you had the longest time for the water, about, let's say, 8 seconds. Second for the ethanol, around 4 seconds, and the oil, it was about 1 second. For the drops on the penny, I'm going to assume that water had the most. Why don't we say about 60, ethanol 40, and oil around 25. Obviously they're different. Some people got more for the oil, but if we took the averages, these would be the predicted amounts. For the density column, the first thing I asked you to do is get the molar mass data. So for water, we know that it was 18 grams per mole. For this one, this would be the same thing as saying C6 or C2H6O. We're going to get, for the C, that's 24, 6, and 16. So that's going to be 46. So this is going to be 46 grams per mole. And for this, we're going to get 12 times 10. That's 120 plus 20, so we're going to get 140 for here. For the density column, we should have ended up with something that had 3 liquids. This one should have been the ethanol. This one was the oil, and this one was the water. If you didn't get that exactly, that's perfectly fine. Given that you have the same volume of each liquid, any prediction here is fine, but a logical prediction that people would have said is molar mass data, rank each liquid in order of increasing density. So I would say that, first we'd say the ethanol. Now a lot of people might have said that the water was next and the oil was after that, since the oil is actually heavier. So this would have been, this relationship right here would have been a common misconception. But just because the alcohol is heavier doesn't mean it's more tightly packed or more dense per se. So for the boiling point, we're going to go ahead and record the boiling points that you guys should have gotten up here. I tried to make this a lot bigger, that's why I'm moving around a little more. So for the ethanol, it was about 80. For the water, it was about 100, and around 140 for the oil. Okay, so what does the vortex time tell you about the strength of the intermolecular interactions? Any guess is fine. So we're going to guess that longer vortex time equals stronger intermolecular interactions. Based on your answer, rank each in order of increasing intermolecular interactions. So, increasing. So this is going to be the lowest, oil is going to be the lowest, and water is going to be the highest. So they wanted it increasing, so we're going to go oil is less than ethanol, which is less than water. Okay, part 2. Drops on a penny. What does the number of drops of liquid on a penny tell you about the strength of the intermolecular interactions? So we're going to say that more drops equals stronger intermolecular interactions. Yay! Okay, based on these, rank them. So let's go up and look at it. And if we look at it, the number of drops on the penny, water had the most, then ethanol, then oil. So they wanted us to rank it in order of increasing, so it's going to be the same as the above. Oil is the least, then ethanol, and then water. Do your answers agree with your answer in part 1? Yes, there is no discrepancy. All right, based on the density column, the information above, do you predict them to have the same intermolecular interactions? So I say that if they dissolve in one another, they have similar intramolecular attractions, and they're soluble in one another. Now they did not dissolve. So it says, based on your density column and the information above, do you predict the 3 liquids to differ in their intramolecular interactions? Yes. Like dissolves like, and they did not dissolve in one another. Thus, they do not have similar intramolecular structure. All right. Draw the Lewis structures for each of the liquids below. Here's the Lewis structure you would end up with for water. Here's the Lewis structure that you would end up with for ethanol. Notice that I'm going to draw this bond right here. I'm going to draw this bent because of the 2 lone pairs on the oxygen. And for oil, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 10. 2, 2, 2, 2, 2, 2. Boom, boom, boom. There it is. Circle the central atom in each structure and use the chart on page 64, 65, and 66 to determine the shape. Draw an arrow to and label the shape of each central atom. All right. So there's the only central atom, and it's called bent. There's a central atom here. Ooh, and we already called it bent. And both of these central atoms are going to be the same, and they're both going to be tetrahedrals. And in this one, this is a tetrahedral, and so are all the other central atoms. These are all tetrahedrals. Now this right here and this right here, those are both trigonal planar. Okay? Yes. They all have different shapes. All right. Boiling point. What does the boiling point tell you about the strength of each of the intermolecular interactions? I'm going to start this part on the next podcast. I'll talk to you guys later. Bye-bye.